December 9th, 1943. 27,000 feet above Emden, Germany. Staff Sergeant Thomas Callahan hunched behind his Sperry upper turret, tracking a Messerschmitt Bf 109 as it rolled into a high-side attack against his B-17. The fighter closed at a combined speed exceeding 500 miles per hour. Callahan's gloved hands gripped the twin .50 caliber machine gun controls, his eyes fixed on the reflector gun sight that glowed dimly in the frozen turret. He led the target exactly as he had been taught, aiming where his training said the enemy would be. His tracers arced harmlessly behind the diving Messerschmitt. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The German pilot pulled through, cannon shells walking across the bomber's right wing. Callahan cursed and traversed the turret desperately, trying to anticipate the fighter's next move. In 6 missions over occupied Europe, he had fired over 3,000 rounds without a confirmed kill. The mathematics haunted him during sleepless nights in the Nissen hut at Bassingbourn. 6 missions, 3,000 rounds, 0 kills. Something was fundamentally wrong with how American gunners were fighting this war. What Callahan could not know, freezing in his turret above the burning city below, was that 1,500 miles away, in a secure laboratory at the General Electric facility in Schenectady, New York, engineers had already solved his problem. Within 4 months, gunners like Callahan would stop trusting their eyes and their training. They would surrender control to electromechanical computers that could calculate in microseconds what the human brain could not process in minutes. They would watch their gun sights move independently of their hands, pointing at empty sky while the guns fired somewhere else entirely, hitting targets they never aimed at directly. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The revolution that would transform aerial gunnery began not with dramatic breakthroughs, but with accumulated desperation. By autumn 1943, the 8th Air Force's losses over Germany had reached crisis levels. During the second Schweinfurt raid on October 14th, 60 B-17 seconds were shot down from a force of 291 aircraft. Another 17 were damaged beyond repair. 650 airmen were dead, wounded, or missing. The gunners aboard the surviving bombers had fired over 2 million rounds of .50 caliber ammunition. Post-war analysis of Luftwaffe records would reveal they had destroyed approximately 25 German fighters, not the 288 they claimed in the heat of combat. The mathematics were brutal and undeniable. American gunners were expending 80,000 rounds for every German fighter actually destroyed. At that rate of exchange, the strategic bombing campaign could not be sustained. Industrial production could replace lost bombers and train new crews, but not fast enough to absorb losses at such catastrophic rates. The problem transcended training or courage. It was fundamentally a problem of physics that human reflexes could not overcome. The difficulty of aerial gunnery had been understood theoretically since the First World War, when observers first mounted machine guns on aircraft and discovered that hitting a moving target from a moving platform at high speed was nearly impossible. During the Great War, fighter pilots had solved this by mounting guns to fire forward through the propeller arc, allowing them to aim the entire aircraft at their target. But bomber defensive gunners had no such luxury. They faced the full complexity of deflection shooting while their aircraft bucked through turbulent air and Rs. German fighters attacked from every angle at closing speeds that could exceed 600 miles per hour. Technical Sergeant Howard Miller, a ball turret gunner with the 91st Bomb Group, attempted to quantify the problem in a letter to his brother, a mathematics professor at the University of Michigan. His calculations, preserved in the university archives, reveal the magnitude of the challenge facing American gunners. Miller wrote that a Focke-Wulf 190 attacking from the 3 o'clock position, perpendicular to the bomber's flight path, presented the gunner with at least 16 variables that needed to be calculated simultaneously. The bomber's airspeed, typically 180 to 220 miles per hour, depending on altitude and bomb load. The fighter's airspeed, generally between 350 and 400 miles per hour during an attack run. The fighter's angle of attack, which changed constantly as the pilot maneuvered, the range to target, which decreased by hundreds of feet per second. The relative wind speed and direction at altitude, which could exceed 100 miles per hour. The gravitational drop of the .50 caliber bullet over distance. The decreased air density at 25,000 feet, which affected bullet trajectory dramatically compared to sea level. The parallax error between the gunner's eye position and the gun muzzle. The temperature, which at altitude could reach 60 degrees below zero and affected ammunition performance. The bomber's own evasive maneuvers, which the pilot initiated without warning to the gunners. The fighter's evasive maneuvers as it approached. The curvature of the bullet's flight path due to the bomber's forward motion. The time lag between the gunner seeing a target and his fingers actually triggering the guns. The mechanical lag in the gun mount's response to control inputs. The dispersion pattern of the bullets themselves, which spread over distance, and the rotation of the turret or gun mount, which added another vector to the equation. No human being can solve this equation in the 2 seconds available, from target identification to firing opportunity. We are asking farm boys from Kansas and factory workers from Detroit to be human calculating machines while being shot at, while freezing, while wearing 50 pounds of equipment in a space barely large enough to turn around. It cannot be done with human reflexes alone. We need the machines to do the mathematics for us. The existing gun sights in use during 1943 were little more than illuminated crosshairs. The N6 reflector sight, standard on most B-17 gun positions, projected a simple reticle onto a small glass plate. The gunner was expected to estimate the target's speed and direction, calculate the necessary lead, and place the reticle ahead of the target by the appropriate amount. This worked reasonably well for slow-moving ground targets in training, but failed catastrophically against German fighters in combat. The fundamental problem was that lead calculation required processing information faster than human cognition allowed. By the time a gunner observed a fighter's position, calculated the appropriate lead, and moved his guns to the predicted intercept point, the fighter had already changed position. The gunner was perpetually aiming at where the target had been, not where it would be. This lag created a hopeless cycle. The faster the fighter moved, the more lead was required. The more lead required, the longer the calculation took. The longer the calculation took, the more the fighter's position changed, invalidating the calculation. First Lieutenant Robert Johnson, a bombardier with the 306th Bomb Group who also manned the nose guns when not on the bombing run, described the psychological impact of this repeated failure in his mission diary. You see the fighter coming. Your brain screams at you to shoot. You track him through the sight, leading him as much as you think necessary. You press the triggers. Your tracers go behind him, always behind him. You adjust, leading more. Still behind. You adjust again, leading even more. Now you are leading so much that you are shooting at empty sky, and it feels completely wrong even though you know it is right. By the time you have finally led enough, the fighter has already made his attack and broken away. You have wasted 200 rounds shooting at ghosts. The solution had been under development since 1942, but only in scattered laboratories with minimal coordination and no sense of desperate urgency. General Electric's Electronics Laboratory in Schenectady, New York, had been experimenting with electromechanical fire control systems since before Pearl Harbor. Sperry Gyroscope Company in Brooklyn was developing automated gun-laying mechanisms for naval anti-aircraft systems. The Johns Hopkins Applied Physics Laboratory was studying proximity fuses and guidance systems. Western Electric was working on radar-directed fire control, but these efforts were disparate, poorly coordinated, and treated as theoretical research rather than operational imperatives. The crisis of autumn 1943 forced sudden coordination. On October 20th, just 6 days after the catastrophic Schweinfurt raid, Brigadier General Lawrence Craigie, chief of the Army Air Force's Engineering Division at Wright Field in Dayton, Ohio, convened an emergency conference bringing together representatives from all these scattered research efforts. The directive was simple and urgent. Develop a gun sight that could calculate deflection automatically and dramatically improve hit rates against German fighters. Time frame for deployment: 6 months maximum. The Manhattan Project had taken theoretical nuclear physics and marshaled industrial resources to build atomic weapons. Now, a similar effort, though vastly smaller in scale, would take theoretical ballistics and create practical computing gun sights. The parallel was not accidental. Several of the scientists involved in gun sight development would later work on nuclear weapons, and they applied similar methodologies. Identify the fundamental physics, reduce it to solvable equations, build mechanical or electronic systems to solve those equations in real time, and test ruthlessly until the system worked under combat conditions. The K-13 computing gun sight emerged from this crucible of necessity. Developed primarily by Sperry Gyroscope Company with contributions from General Electric and the Army Air Force's Material Command, the K-13 represented a fundamental reimagining of what a gun sight could be. Instead of a simple optical device that showed where the gun was pointing, it became an analog computer that calculated where the gun needed to point to hit a moving target. The physics behind the K-13 were understood in principle, but fiendishly difficult to implement mechanically. The sight needed to measure target range continuously, using a combination of optical range finding and the gunner's manual input. It needed to measure the target's angular velocity across the sky as the gunner tracked it. From these measurements, it needed to calculate the target's actual velocity vector in three-dimensional space. It then needed to calculate the time of flight for the bullet to reach the target's future position. Using this time of flight, it needed to calculate where the target would be when the bullet arrived. It needed to account for the bomber's own velocity, which added to the bullet's velocity in the direction of flight but created complex cross-range effects. It needed to account for gravitational drop over the bullet's flight time. It needed to account for air density at altitude. And it needed to do all of this continuously, updating its calculations multiple times per second as both aircraft maneuvered. The K-13 accomplished this through an ingenious combination of gyroscopes, mechanical integrators, and servo motors. The gunner placed a small aiming pip on the target and tracked it. As he tracked, gyroscopes in the sight measured the angular velocity of his tracking motion. Mechanical computing elements, essentially specialized gear trains and cams, converted this angular velocity into predicted target motion. The computer calculated the appropriate deflection and automatically moved the gun to the computed firing point. The sight reticle showed where the gunner was aiming, but the gun pointed somewhere else entirely, at the mathematically calculated intercept point. Captain Arthur Davidson, one of the Sperry engineers who designed the K-13's mechanical computing elements, later described the device's operation in a 1946 technical paper. The gunner believes he is aiming at the target because his sight reticle remains centered on the target aircraft. What he does not see is that the gun itself is aimed at a point in empty space ahead of the target, sometimes by as much as 30 or 40 degrees. The computer is doing the deflection calculation automatically based on his tracking motion. He simply keeps the target centered in his sight and presses the trigger when the target is in range. The mathematics happen invisibly. The first prototype K-13 sights arrived at Eglin Field, Florida, in early December 1943 for initial testing. The testing protocol was rigorous and designed to simulate combat conditions as closely as possible. Radio-controlled target drones simulated German fighter attacks at realistic speeds and approach angles. Gunners fired from turrets mounted in the waists of B-17 seconds that flew at operational altitudes. Temperature was controlled to match the extreme cold of combat altitude. Gunners wore full combat equipment, including oxygen masks, flak suits, and gloves. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The initial results were mixed and concerning. The K-13 dramatically improved hit rates when it worked correctly. but the mechanical complexity made it temperamental. Cold temperatures caused lubrication to congeal, making the gyroscopes sluggish. Vibration from gun recoil sometimes disrupted the delicate mechanical computations. The optical range-finding system struggled in poor visibility conditions. Most concerning, the sight required electrical power from the bomber's generators, and if power was interrupted, the sight became useless, leaving the gunner with no backup capability. Master Sergeant Vincent Delorio, a gunnery instructor assigned to the Eglin Field Testing Program, remembered the early frustrations. The first K-13s were magnificent when they worked, and absolutely worthless when they did not. In laboratory conditions, they were miraculous. Gunners with minimal training were hitting targets they could never have hit with conventional sights. But introduce real combat variables: cold, vibration, electrical problems, battle damage, and the failure rate was unacceptable. We knew we had the right concept, but the engineering was not yet ready for operational use. The engineering refinements consumed the winter of 1943 into 1944. Sperry engineers worked around the clock, addressing each failure mode. They developed cold-resistant lubricants that remained fluid at 60 degrees below zero. They ruggedized the gyroscope mountings to withstand sustained vibration. They simplified the mechanical computing elements to reduce points of failure. They added backup iron sights that would remain functional even if electrical power failed. They developed training protocols so gunners would understand both how to use the sight and how to revert to manual aiming if it malfunctioned. By February 1944, the K-13 had evolved from a promising prototype to a combat-ready system. The Army Air Forces ordered immediate production with priority ratings that diverted manufacturing capacity from other programs. Sperry's Brooklyn factory began producing K-13s at a rate that would eventually reach 500 units per month. Installation priority went first to turret positions, where the confined space made manual deflection calculation most difficult, then to waist positions, and finally to tail positions. The first operational K-13s reached England in mid-March 1944. The 91st Bomb Group at Bassingbourn received the initial allocation of 50 sites, enough to equip half their aircraft. Installation crews worked through the night, removing old N6 sites and installing the new computing systems. Electrical technicians ran new wiring to provide power. Armourers calibrated each site to match the specific ballistic characteristics of the aircraft's ammunition load. The training program for operational gunners was necessarily compressed. Technical Sergeant Robert Hendricks, who received K-13 training at Bassingbourn in late March, described the process as simultaneously simple and bewildering. The instructors told us to forget everything we knew about leading targets. They said the sight would do the leading automatically. Our job was simply to track the target smoothly and keep it centered in the reticle. If we tracked smoothly, the computer would calculate the correct deflection. If we tracked erratically, the computer would give erratic solutions. They emphasized that we needed to trust the mathematics, even when our instinct screamed that we were aiming at the wrong place. The combat debut came on March 22, 1944, during a maximum effort mission against German airfields in southern Germany. 18 B-17 seconds, equipped with K-13 sights, flew as part of a larger formation of over 400 bombers. The mission encountered heavy fighter opposition, with Luftwaffe fighters making over 300 individual attack passes at the American formations. The results from the K-13-equipped aircraft were immediately apparent. The 18 aircraft equipped with the new sights claimed 31 fighter kills, later confirmed by gun camera footage and Luftwaffe loss records as 23 actual kills. This represented a hit rate of approximately 7%, meaning 1 bullet in 14 found its target. The remaining aircraft, equipped with conventional sights, claimed 87 kills, later confirmed as 19 actual kills, a hit rate of barely 2%. More significantly, the K-13-equipped aircraft suffered proportionally lower losses. 2 of the 18 were shot down, an 11% loss rate. The conventional aircraft suffered 38 losses from 382 aircraft, a 10% loss rate that would seem similar until analysed more carefully. The K-13 aircraft had flown in more exposed positions because they were deliberately placed where fighter attacks would be heaviest to test the new sites under maximum stress. Adjusted for position in formation and exposure to fighter attacks, their survivability was nearly double that of conventionally equipped aircraft. Staff Sergeant Thomas Callahan, the same gunner who had missed repeatedly in December, flew his first mission with a K-13 on March 22. His after-action report captured the psychological transformation. I tracked a 109 making a 12 o'clock high attack, kept him centered in my sight, just as training said, and pressed the trigger. I was not aiming at him in the traditional sense. The reticle was on him, but I could see my tracers going far ahead of him, seemingly into empty air. My brain screamed that I was missing. Then he flew directly into my bullet stream. I watched pieces fly off his wing. He rolled, inverted, and went down. I'm smoking. I had shot him down by aiming somewhere I could not even see him. The mathematics had worked, despite every instinct telling me I was wrong. The 8th Air Force immediately accelerated K-13 deployment. By April, production had increased to 800 sites per month. By May, over 1,000. Installation crews worked continuously, modifying aircraft as quickly as sites arrived. Priority went to groups flying the most dangerous missions, deep penetrations into Germany, where fighter opposition remained fierce. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The impact on German fighter tactics was profound and forced immediate adaptation. Luftwaffe pilots had developed sophisticated attack patterns based on exploiting the limitations of American defensive fire. They knew American gunners struggled with high-speed deflection shooting. They knew that attacks from certain angles, particularly high-side passes at high speed, were very difficult for gunners to counter effectively. These tactics had been refined through thousands of combats and were taught systematically at Luftwaffe fighter schools. The K-13 invalidated much of this tactical doctrine. American gunners with computing sights were hitting fighters at ranges and deflection angles that had previously been safe. Hauptmann Heinrich Sturm, flying with Jagdgeschwader 26, noted the change in a tactical report dated April 19, 1944. American defensive fire has become significantly more accurate in recent weeks. Attacks that previously could be made with acceptable risk now result in hits even when we maintain high speed and maximum deflection. Their gunners appear to be leading us correctly even at extreme angles, where calculation should be impossible. We are suffering increased losses from defensive fire and must revise our attack procedures accordingly. The German response took multiple forms. Luftwaffe fighter units began emphasizing even higher speed attacks, trying to reduce exposure time to absolute minimum. They increased use of heavy cannon armament, trying to destroy bombers from beyond effective defensive gun range. They developed the Sturmgruppe concept, heavily armored fighters designed to press attacks to point-blank range, where even computing sights could not compensate for the sheer momentum of the attacking aircraft. Most significantly, they began avoiding beam attacks, the perpendicular passes where computing sights were most effective, and instead emphasized head-on and tail attacks where deflection angles were smaller. The evolution of American gunnery doctrine continued rapidly through spring and summer 1944. The K-13 was just the beginning. The K-14 sight, introduced in June, added radar ranging to eliminate the need for optical range estimation. The K-15, which entered service in August, incorporated automatic lead computing for multiple targets simultaneously. Each generation increased complexity, but also increased effectiveness. Technical Sergeant James Morrison, who had attempted to solve the gunnery problem mathematically in his notebook, finally received a K-13 in May 1944. His reaction captured both the power and the strangeness of computing sights. For months I had been trying to calculate manually what this sight does automatically. I had filled notebooks with equations trying to solve for deflection angles. Now I simply track the target and the sight does in microseconds what I could not do in minutes. It is both humbling and liberating. Humbling because it proves how inadequate human calculation is for this problem. Liberating because it finally gives us a weapon that works. But there is something unsettling about surrendering control to the machine, about trusting mathematics you cannot see or verify. The psychological dimension of computing sights went deeper than mere trust in technology. Traditional marksmanship connected the shooter directly to the target through the sight picture. The marksman saw the target, calculated the lead, aimed, and fired. Success or failure was directly attributable to the shooter's skill. Computing sights broke this direct connection. The gunner saw the target, tracked the target, but the actual aiming was done invisibly by mechanical calculators. Success depended on the machine's mathematics being correct and the gunner's tracking being smooth, but the causal connection between action and result became abstract. Some gunners struggled with this abstraction. Second Lieutenant Arthur Goldman, a bombardier who also manned nose guns, wrote to his wife about the difficulty of trusting the computing sight. Every instinct developed through years of shooting tells you to aim at where you think the target will be. The computing sight removes this judgment from you. You simply track, and the machine aims. When you score a hit, you do not feel like you aimed well. You feel like you tracked adequately, and the machine calculated correctly. The satisfaction of marksmanship is diminished. You become less a shooter and more an operator of a shooting system. It is effective but somehow less human. The transformation of gunnery training reflected this shift from marksmanship to system operation. At the flexible gunnery schools in the United States, the curriculum underwent radical revision. Traditional marksmanship fundamentals, breath control, trigger squeeze, sight picture, were compressed into a brief introductory module. The bulk of training now focused on smooth tracking, understanding the computing sight's operation, recognizing when the sight was functioning correctly, and knowing how to revert to manual aiming if the computing system failed. The WWII gunnery trainer, the sophisticated electromechanical simulator that had been reprogrammed for zone firing just months earlier, was modified again to teach computing sight operation. Now it rewarded gunners who tracked targets smoothly and consistently, allowing the simulated computing sight to generate accurate firing solutions. Erratic tracking, even if the gunner managed to keep the reticle on target, resulted in poor scores because it disrupted the sight's calculations. Master Sergeant Frank Rodriguez, the same gunnery instructor who had overseen the transition to zone firing, now oversaw the transition to computing sights. The evolution has been extraordinary. In early 1943, we taught traditional aimed fire and individual marksmanship. By late 1943, we taught zone firing and statistical probability. Now, in 1944, we are teaching system operation and trust in automated calculation. Each transformation has moved us further from individual skill and closer to being components in a larger technological system. The most effective gunner is no longer the best shot. He is the one who operates the computing sight most effectively. The statistical impact of computing sights became undeniable by summer 1944. The 8th Air Force Operational Research Section compiled comprehensive data comparing aircraft equipped with computing sights to those with conventional sights. The analysis, classified secret and distributed only to senior commanders, documented a revolution in aerial gunnery effectiveness. Aircraft equipped with K-series computing sights achieved fighter kill rates averaging 6.3%, meaning 1 bullet in 16 hit the target. This compared to 2.1% for conventional sights using zone firing techniques and just 0.5% for traditional aimed fire. Computing sights had increased effectiveness by a factor of 12 compared to the techniques used just 1 year earlier. More importantly, bombers equipped with computing sights survived their missions at significantly higher rates. The average loss rate for computing sight-equipped aircraft was 4.2% per mission compared to 6.7% for conventionally equipped aircraft. Over a 35-mission combat tour, this difference was enormous. A gunner on a computing sight-equipped aircraft had a 64% probability of completing his tour. A gunner on a conventionally equipped aircraft had only a 43% probability. The computing sight was not just more effective at destroying German fighters, it was directly saving American lives in measurable, quantifiable numbers. Colonel Curtis LeMay, who had pioneered combat box formations and would later lead the strategic bombing campaign against Japan, immediately grasped the strategic implications. In a memo dated June 15, 1944, he wrote that computing sights represented a decisive technological advantage that needed to be exploited immediately and completely. He recommended that all B-17 and B-24 production aircraft be equipped with computing sights as standard equipment, and that all existing aircraft in combat theaters be retrofitted on a priority basis. The loss rate differential alone justified diverting whatever manufacturing capacity was necessary. The production and logistics challenge was substantial but manageable given American industrial capacity. By July 1944, Sperry was producing 1,200 K-series sights monthly. Western Electric had begun producing a competing design, the Mark 15, at a rate of 800 units monthly. General Electric was developing the K-16, which would incorporate miniaturized radar components. The combined production rate would reach 3,000 computing sights per month by autumn, enough to equip all heavy bombers in all theaters, plus provide reserves and training equipment. The installation logistics required coordination across multiple organizations. Modification centers at Burtonwood, England, and Cheyenne, Wyoming, installed computing sights on aircraft already in service. New production aircraft from Boeing, Douglas, and Lockheed Vega incorporated computing sights during manufacture. Training centers received computing sights for instructional use. The entire supply chain, from component manufacturing through final installation and crew training, had to be coordinated to ensure that sights, aircraft, and trained crews all came together at operational bases simultaneously. By August 1944, approximately 60% of 8th Air Force heavy bombers were equipped with computing sights. By October, over 85%. By the end of the year, virtually every American heavy bomber flying combat missions in Europe carried computing sights in at least some gun positions, typically upper turrets, tail positions, and ball turrets where they were most effective. The tactical impact extended beyond immediate hit rates. Computing sights changed how bomber formations defended themselves. With conventional sights, tight formations were essential to create overlapping fields of fire and mutual support. The density of defensive fire from multiple aircraft compensated for individual inaccuracy. Computing sights allowed formations to loosen slightly because individual aircraft could defend themselves more effectively. This looser spacing reduced the risk of collision during combat maneuvers and made formations less vulnerable to German rocket attacks, which relied on the tight spacing of bomber formations to ensure hits within the rocket's blast radius. Mission planning evolved to exploit computing sight capabilities. Planners could route formations through areas of heavy fighter opposition with greater confidence that defensive firepower would be adequate. They could reduce escort fighter allocations for certain mission profiles, freeing long-range fighters for other tasks. They could accept slightly higher altitudes where cold temperatures had previously caused conventional sights to perform poorly, but where computing sights, properly winterized, functioned reliably. The German countermeasures continued evolving. Unable to defeat computing sights through tactical adaptation alone, the Luftwaffe increased emphasis on technological solutions. The Messerschmitt Me 262 jet fighter could attack at speeds where even computing sights struggled to generate accurate solutions. The R-4M rocket, fired from beyond effective gun range, allowed fighters to attack without entering defensive fire zones. The Schräger Musik upward-firing cannon installation allowed night fighters to attack from directly below, where most bombers had no defensive armament regardless of sight technology. But these countermeasures came too late and in too small quantities. By autumn 1944, Germany's industrial capacity was collapsing under relentless bombing. Fighter production, though still substantial, could not replace losses. Experienced pilots were becoming scarce as training programs were disrupted and fuel shortages limited instruction hours. The few advanced weapons that reached operational units could not compensate for systemic collapse of the Luftwaffe as an effective fighting force. Technical Sergeant Robert Hendricks, who had received K-13 training in March, flew his 35th and final mission on September 23, 1944. His final mission report noted that he had destroyed 5 German fighters and damaged 7 others using computing sites. He had fired approximately 14,000 rounds total during his combat tour. With an average of 900 rounds per damaged or destroyed aircraft, his efficiency was nearly 10 times better than gunners had achieved 1 year earlier. More importantly, he had survived. Computing sites had been a major factor in that survival. The B-29 Superfortress, entering service in the Pacific Theater in late 1944, represented the ultimate expression of computing site technology. Its central fire control system integrated computing sites with remotely operated turrets and a sophisticated analog computer that coordinated all defensive armament. The gunner merely designated targets. The computer calculated firing solutions, aimed all guns that could bear on the target, and fired automatically when the solution was optimal. It was the logical endpoint of the revolution that had begun with the K-13, complete automation of aerial gunnery with human operators reduced to target designation and system monitoring. Major William Becker, the former MIT physics professor who had analyzed B-17 combat footage and advocated for zone firing in 1943, observed B-29 operations in the Marianas in early 1945. His assessment captured both the power and the implications of automated fire control. We have achieved what seemed impossible just 2 years ago. We have removed human reflexes and human calculation from the gunnery equation entirely. The B-29's fire control system aims and fires faster and more accurately than any human gunner could. But we have also removed humanity from the process. The gunner is no longer a warrior exercising skill and courage. He is a systems operator, a component in a larger mechanism. We have won through technology, but we have transformed the nature of combat itself in the process. The final missions of the European war demonstrated how completely computing sites had transformed aerial combat. On April 10, 1945, over 1,000 B-17 seconds and B-24 seconds struck targets across Germany. Despite desperate Luftwaffe resistance that included jet fighters and rocket-armed interceptors, only 8 bombers were lost. The defensive firepower of formations equipped with computing sites had become so effective that attacking them was virtually suicidal. German fighter pilots, even those flying advanced aircraft, faced walls of accurately aimed fire that made successful attacks impossible. Lieutenant General James Doolittle, commanding the 8th Air Force, assessed computing site effectiveness in his final report dated May 20, 1945. The introduction of computing gun sights represented one of the most significant technological advantages achieved during the air campaign. These devices increased gunner effectiveness by factors measured in hundreds of %. They reduced bomber losses measurably and significantly. They forced the enemy to expend resources on countermeasures that diverted effort from other priorities. Perhaps most importantly, they saved thousands of American lives by allowing our crews to defend themselves effectively. The computing sight was not merely a better gun sight, it was a war-winning weapon. The post-war analysis by the United States Strategic Bombing Survey examined computing site impact in detail. The survey concluded that computing sites had been instrumental in achieving air superiority over Germany. By increasing bomber survivability and reducing losses, computing sites had enabled the sustained bombing campaign that destroyed German industrial capacity. By forcing the Luftwaffe to adapt tactics and develop countermeasures, computing sites had imposed additional strain on German resources. The survey estimated that computing sites had prevented approximately 1,200 bomber losses, saving over 12,000 crew lives, and conserving bombers worth over $500 million at wartime prices. The financial return on investment was extraordinary. The entire computing site development program, including research, development, testing, production, and training, cost approximately $75 million. The bombers saved were worth nearly 7 times this amount. The trained crews saved represented years of training investment. The strategic value of maintaining a sustainable bombing campaign was incalculable. By any measure, computing sites represented one of the most cost-effective technological investments of the entire war. The technical legacy extended far beyond World War II and influenced military technology for decades. Every subsequent fire control system, from Korean War-era radar directors to modern computerized weapon systems, traced conceptual ancestry to the K-13 and its successors. The principle of using automated calculation to solve problems too complex for human reflexes became fundamental to military technology. Modern fighter aircraft, naval vessels, ground vehicles, and even infantry weapons incorporate computing elements that calculate firing solutions automatically. The soldier or sailor still designates targets and authorizes engagement, but the machine calculates how to achieve hits. The human legacy was equally profound. Approximately 176,000 aerial gunners served in American heavy bomber units during World War II. Of these, approximately 90,000 used computing sites during at least part of their combat tours. These men experienced firsthand the transition from human skill to machine calculation, from individual marksmanship to automated fire control. Many struggled with the psychological implications of surrendering control to technology. Most recognized that the technology saved their lives. All participated in a fundamental transformation of warfare. Veterans consistently emphasized the strangeness of fighting with computing sites. At reunions and in oral history interviews, former gunners described the uncanny feeling of scoring hits by aiming at empty space, of trusting mathematics they could not verify, of becoming operators rather than warriors. Staff Sergeant William Patterson, who flew 35 missions as a tail gunner, reflected decades later that the computing site had made him more effective but somehow less engaged. You felt disconnected from the fight because the machine was doing the aiming. You tracked targets and pressed triggers, but the actual shooting was automated. It saved your life, but it also diminished your sense of personal agency. The ethical dimension of automated weapons emerged even during World War II. Some observers worried that removing human judgment from targeting decisions, even to the limited extent represented by computing sites, represented a dangerous precedent. If machines could aim guns, what would prevent them from selecting targets and firing autonomously? The debate would intensify in subsequent decades as weapon automation advanced, but the fundamental question was already apparent in 1944. How much control should be surrendered to machines? Where is the boundary between useful automation and dangerous abdication of human responsibility? These questions remain unresolved in the 21st century, as artificial intelligence and autonomous weapons systems become increasingly sophisticated. But they trace directly to that moment in 1943, when American engineers decided that human reflexes were inadequate for modern combat and began building machines to replace human calculation. The K-13 computing site was a crude analog computer by modern standards, but it represented a conceptual leap that continues to shape military technology. Today, several B-17 seconds remain airworthy, maintained by museums and historical organizations. Visitors can examine the turrets and gun positions where computing sites once gave American gunners decisive advantages. The sites themselves are rare. Many were removed and scrapped after the war. Those that survive in museum collections are treasured artifacts, representing a pivotal moment in military technology, when mathematics became weaponized, when calculation became as important as courage, and when machines began taking over functions previously performed by human judgment. The story of computing sites is ultimately about adaptation, innovation, and the complex relationship between humans and technology in warfare. American forces faced a problem: inaccurate defensive gunnery that was causing unsustainable losses. Traditional solutions, better training, more practice, improved marksmanship instruction, had failed because they addressed symptoms rather than causes. The fundamental problem was not that gunners were poorly trained. It was that the task exceeded human capabilities. No amount of training could make human reflexes fast enough or human calculation accurate enough to solve deflection problems at high speed. The solution required accepting human limitations and building technology to overcome them. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.